I am the session chair. So I see we have 3 talks. Each one will be something like 20 to 25 minutes plus 5 to 10 minutes for questions. The first talk is on learning quantum channels without input control, and the speaker is Matteo Rosati, please.
Hi everyone. Good good afternoon, good morning, good night, wherever you are. Thanks. Let me thank the organizers for allowing us to present our work today. This is work done by Marco Fanizza from Barcelona, Juhe Kwek from Berlin, and I. And it's going to be on archive soon, probably this week or next week. So check it out. It's a work where we study learning theory for processes in a setting where you do not have control over the training samples. So you're not free to choose identical copies of your quantum states to train over. So I'm going to do a bit of a background on classical statistical learning theory and some attempts at generalizing it to quantum systems. Then I'm going to present our problem, whose key motivation, let's say, and difference with respect to previous works is tackling the case of non-identical training samples. And I'm going to discuss our main result and the methods that we use. We combine some methods from classical theory and some quantum works on quantum systems done before. And in particular, we generalize this instrument threshold search to the case of non-identical product source. Finally, I'm going to discuss a couple of applications because we believe this is a step forward in applying, let's say, this new machinery from statistical learning theory to problems which are maybe a bit less motivated by computation, but more by statistical inference methodology. Okay, so let's say machine learning works very well by now, but the theory behind it was started very early, actually by Vapnik and Chervonenkis in the 70s. And I'm going to review it here using a review by Vapnik himself. He was basically interested in studying statistical inference in very high dimensions. And the tale goes as follows. So we have an unknown function mapping from an input domain X to an output domain Y. And we have class candidates or hypotheses, if you want, which are also functions from X to Y. We are given some training samples. These are composed of input samples of the input variable X, sampled according to a probability distribution, which is potentially also unknown, and the corresponding output associated by applying the unknown function to a given sample of X. We want to find essentially a good candidate, a good hypothesis inside the class that somehow approximates the function. What does it mean to be good? Okay, so we can come up with a loss function, essentially the performance of our candidate and the unknown function. And then we can consider this object, which is called the true risk of the hypothesis G, which is essentially the expectation of the loss with respect to the unknown probability distribution. In practice, we cannot really compute this. We have access, however, to the so-called empirical risk, which is essentially the average of the loss with respect to the sample that we are seeing, that we're working with. So the objective is to find a candidate for which the empirical risk, R hat, is close to the minimum true risk over the candidate class, the function class. We allow for some error, and this is going to happen with high probability. Now, Vapnik and Chervonenkis provide a solution, if you want, in 2 steps. One is an asymptotic guarantee. This asymptotic guarantee is telling you that learning is possible if and only if this condition is satisfied. Now, this condition essentially says that this quantity gamma that I'm going to explain and to talk about later on grows sufficiently slowly with the sample size n. This is a quantity that characterizes the, if you want, the richness of your hypothesis class, and also how difficult it is to identify a good candidate in there. Okay, the second result is a non-asymptotic result. It says, okay, if this condition holds, you can actually learn with a finite number of samples, which is characterized by satisfying this condition. So essentially, in most results, you will find about statistical learning theory, this quantity scales as a power of the sample size with an exponent that is a dimension. It's called a dimension. In particular, for binary output functions, this is the celebrated VC dimension that, again, somehow characterizes the complexity of this function class. Okay, now let's look quickly at a couple of examples from quantum information theory. The most popular attempt at generalizing this to quantum systems was made by Aronson in 2018. It's called shallow tomography. In this case, you're given n copies of a quantum state that you don't know. And using these copies, you want of a certain number of binary measurements. So you can think of these as projectors by a simple dilation argument. And we have m of them, and we want to estimate their expectation on the unknown state rho. So essentially, we want to find a good candidate sigma such that the expectation on this sigma of each of the measurements is close to the true expectation on the unknown state. Aronson provides a strategy to do this, which is collective. It operates collective on the whole number of copies, and it works with a sample complexity, which importantly scales as the logarithm of the number of measurements and the logarithm of the system dimension. Why is this interesting? Because for full tomography, you would need d squared, and then you would be able to predict everything. Whereas if you wanted to try to estimate each expectation separately, you would need m, something scaling with m. Instead, you're able to do this faster, let's say. How does this compare with the classical setting that I've introduced before? Well, we could say that you're trying to learn a function that maps from measurements to their acceptance probability on the unknown state. However, note that here we have a finite number, whereas before I was supposing to have a potentially infinite number. Okay, and of course I'm given access to the copies of the same quantum state each time. The second work I want to mention is the work by Huang et al. From this year. And this is an upgrade. Now you have access to n uses of an unknown quantum circuit, which are promised this polynomial depth. So near term in a sense. And then your, sorry? Your objective is to find a good candidate which reproduces accurately the output of this quantum channel on average with respect to the input taken according to an unknown probability distribution. So in this case, you can manipulate, if you want, these n uses of the channel as you wish. You can choose your inputs and choose your collective output measurements. And the sample complexity, again, scales logarithmically with the system dimension. Again, how does this compare with the classical case? Well, here you are actually trying to learn a process that maps quantum states to other quantum states. However, note that you have full control over the input, basically. So there is no real variation over the samples, no probability distribution over the samples that you're getting. You assume that you can produce as many copies as you want of the quantum channel with a given input. And that's what we want to avoid in our setting. So our aims are, first of all, full generalization of the classical theory for classical quantum processes. in particular, we are interested in having training data which are truly random. You're not free to choose them. To tackle the cases where you have a potentially infinite number of values that you want to approximate, of outputs of the function, and also potentially infinite number of candidates that you can choose from. So the idea to tackle this is to consider a source, an unknown source. This maps a classical random variable x to a quantum state which depends on x. You have access to n uses of this source, but you cannot choose the inputs, importantly. So they're basically sampled at random according to a probability distribution. And then you can perform a collective measurement with the task of finding a good approximation of the classical quantum process itself, and that maps x to rho of x. A bit more formally, we have these functions which again map from an input x to the space of density operators of a Hilbert space, and we're going to consider a couple of classes. Projector valued class, so the hypotheses here are essentially projectors. So for example, pure states, and the loss function is just 1 minus the acceptance probability of that projector on the unknown state. We can also consider mixed states. So we can also consider a class of state-valued functions, and in this case, we take as a loss the trace distance. Okay, so now we're given samples of the classical variable x and the corresponding output, rho of x, and we want to find a good candidate that is an operator valued function in the class whose empirical risk is close to the minimum true risk inside the class. I want to stress also that we are in the so-called agnostic setting where the true function or the true state does not necessarily live inside the space of the candidates. So in general, you're not promised to have a hypothesis which is correct, but you want to find an approximately correct hypothesis, okay, inside your class. So now the main result is a sufficient condition for learnability in the sense that I've described above, which is governed again by this gamma function. It's similar in spirit to the result of Vatnik. And this gamma is a covering number, which is roughly defined as a number that counts the minimum number of functions that you need to approximate every function in C, in the hypothesis class, when it is applied to an arbitrary sample of size n. So basically, for each sample, x, we want to construct a cover, this C tilde of x, with the property that when I pick an operator inside C, there is also another operator in Cx that is epsilon close in some operator norm on average with respect to the sample that I'm looking at. Okay, so I'm going to discuss a bit more in detail what are the techniques that we use. So I'm going to focus for the rest of the talk, let's say, on pure states or projector valued classes. You can look at the state proof in the paper, but it's just, let's say, an incremental step. You need just another step on top of pure states. But the core ideas are the same. So basically, there are 3 main points. The first is the core of the quantum routine that we use to learn these processes, which is called quantum threshold search. This has been studied, tackled in several fashions throughout the years. For example, I cite Aronson and Badescu and O'Donnell. In particular, we generalize the results of Badescu and O'Donnell to the case of non-identical states, which is slightly more difficult. Then this object, this method is used iteratively to essentially perform an estimation of the minimum empirical risk. And then we have to combine this with a classical result which is the traditional result by Vapnik and Chervonenkis, that ensures that the empirical risk converges to the true risk. So let's start from the last part, the classical part. Now, let's imagine we have a slightly easier problem. Here, you're given a fully classical sample. So basically, the classical variable is X and it's sampled according to the probability distribution. And then you have a classical representation of the quantum state corresponding to that input. Okay? Why this? Well, because it's easier, because if you have a classical representation, you can estimate the risk for all your projectors at once, right? Because you don't need to spare your copies. You don't have non-commutation problems. This is just a classical representation of rho, so you can in principle estimate all these quantities. And then what you do is minimize the empirical risk. Now, a non-trivial fact, it will maybe seem a bit trivial because I'm saying this quickly, but it took quite some time to do it, is that these empirical risks converge to the true risks sufficiently fast, let's say. So the guarantee of this uniform convergence result is that essentially the probability of any outliers for which the empirical risk deviates more than epsilon from the true risk is exponentially suppressed, provided that this covering number of the function class grows sub-exponentially, essentially with the sample size. Okay. Note that this is not just a trivial union bound, because you will need to put here the number of projectors. So this gamma is really quantifies. It's a more clever way to quantify the effective size of your class, which does not boil down only to the number of elements it contains. Okay. Now the quantum part is motivated by some problems. Okay, so the first problem is this one. Suppose we have this objective of estimating now the minimum empirical risk, because we know it converges to the true risk. First problem is that this function class potentially is infinite. This is a problem that takes place also in the classical theory. So you cannot possibly think of estimating the risk for actually all your candidates. And what you do is you build a covering, as I was explaining before. So this is kind of solved. The second problem is that these operators, even the ones inside the cover, will not commute in general. We have access now only to quantum copies. And so we cannot estimate all these risks at once because they do not commute. And for this, we use this quantum threshold search. So I'm going to describe directly our generalization, which is in the spirit of this workshop, at least one I from non-IID. So we're going to consider that we're given these samples, which are non-identical copies. They are in a tensor product. And okay, but it's going to have a way of measuring projectors when these states are the same, are n copies of a single state. In this case, we don't have the luxury of this. What we want to do is we're given classical knowledge of gamma projectors, and we're promised also that there are some thresholds. We're given some thresholds, and at least one of these is true. What does it mean? It means that the acceptance probability of, for example, pi1 on average with respect to the sample is larger than the given threshold. Given this promise, it's possible to show, we show that there is an algorithm that outputs with some finite probability either a label of a projector which actually is above threshold, so it finds one of the projectors which is above threshold, or it declares failure. It says, okay, all of them are below threshold. There is a way, of course, we show technically how to control the false negative and false positive probabilities. And the important thing is that this procedure uses only a number of samples which is logarithmic in the number of projectors. So again, as I was saying, these projectors might not commute. So how does this work? You might guess that it works using a weak measurement. So the idea is that you want to estimate these expectation values, let's say, for each candidate. So I'm going to call this TJ. And the weak measurement basically checks whether these, for a given J, TJ is above threshold up to the addition of some exponential noise, okay? With this mechanism, we ensure that if we obtain that J, we obtain a yes result, J is above threshold, then we can break the cycle. Basically, we don't need to use the quantum state anymore because we have identified a candidate which is good, okay? Instead, if the measurement outputs a no, then we want to reuse the state, the post-measurement state, to try and test the next threshold, okay? And that's the key of this exponential noise mechanism that allows a weak measurement until you find a good candidate. Okay, so with this instrument, we're basically almost done. Then it's a matter of thinking, what do you do when you don't have the thresholds? So if you don't have the thresholds, you start with random ones and you perform essentially a binary search and some safety tests that ensure that error probability is controlled. And with this, we basically obtain the convergence theorem, and we obtain the complexity result that I presented. Okay, now I'm going to talk about a couple of applications. How am I doing with time?
I think you're doing pretty well.
Okay, cool.
I have a few minutes.
So,
yeah.
Nice. Then our results apply also to an improved version of shadow tomography. I won't talk about it, but you can look at it in the paper. We want to discuss some applications that we analyze in our paper, which motivate a bit more the framework that we studied. So as I was saying before, this kind of reasoning has been applied recently more to the computational side of quantum information theory, where you suppose that you are kind of training a circuit and these samples come kind of free. You can produce as many as you want. And so you don't really have the problem of these samples, which if you want to change according to a parameter. Whereas in settings motivated by metrology, this is much more reasonable. So it's much more user-friendly for an experiment where you're observing a process and want to learn something about it. So just a couple of ideas. An idea from imaging. Imagine you have a sample with some spatial profile, and depending on the position inside the sample, there is a different height. So the objective will be to learn this height profile. This is a function, an arbitrary function, and we illuminate the sample, and by a random process, we see photons, for example, coming back from a given position. It's a random process, so we do not really control which position the photon will come from. So I look at the first sample and I see that in this position, I see a certain state of the photon. And then I illuminate again and I get another state depending on another position. And the dependence is encoded by some optical properties that depend on the height of the profile. For example, the optical path length. So we want to learn this height profile as a function of the position. The function class that we consider, that we propose, is this one. You can imagine, for example, that U is a phase, and basically, the larger the height of the sample at a certain position, the larger the phase that gets accumulated on the photon. We compute the complexity of this class, and it essentially depends on this dimension, big D, which is the classical statistical dimension of the function class where your several height profile candidates come from, and also logarithmically on the dimension of the system. Another example is an example of Hamiltonian learning. This is, again, just a motivation from a theorist. Just imagine you have an atom in a cavity, and there is a magnetic field which varies, and maybe you want to you're able to measure this magnetic field. And depending on the field, the energy levels of the atom change. And you can observe this system by measuring photons that come out from the cavity. So for each value of the field, which may change or fluctuate in time, I get a different quantum state of the photon. So we want to learn, in this case, the excited state energy as a function of the magnetic field. So as a function class, we can take projectors on the energy levels of a Hamiltonian, which is perturbed, and the perturbation is a functional, has a functional dependence on B that we want to learn. This task has the same complexity as the one before. Finally, I'm going to mention also that we, of course, have some more applications related to circuits. In this case, you can imagine that you are you want to try to imitate an unknown circuit that depends on some classical inputs. So you want to compile it in your architecture. So you want to learn the circuit as a function of the classical parameters that encode some information into it. And also in this case, we have a projector valued class essentially, and the complexity also depends on the depth of the circuit. So in conclusion, we introduced the general learnability condition and framework for processes where you cannot control the input and the map classical variables to quantum states. We used as a technical tool generalization of quantum threshold search to non-identical sources, plus some insight and combination from the classical results. And we believe that this is a nice user-friendly framework for learning from noisy or random experiments. And I tried to convince you in the end about a couple of applications that might be motivating to investigate further. Let me just mention that similar approach to this one was taken by Caro and Chung Lin. They studied very specific, what we can call very specific instances of our problem. In the case of Caro, just binary output processes, and in the case of Chung Lin, the case where your candidate is actually inside, where your unknown function is actually inside the candidate class. We believe this is a more comprehensive treatment of the problem, but I encourage you to look at their papers as well. Thanks very much for your attention.
Thank you very much. So, yes, Mark has a question.
Hi, Matteo. Thanks for a very
Hi, Mark.
interesting talk. Can you go to the 2 slides forward from the bottom about compiling?
Yeah.
Can you, yeah.
Sure.
So why is this class C a projection value class?
So because I imagine that I'm doing a pure measurement, a projective measurement, if you want.
I see. It's so
So pi is a projector. You can fix it. You can think it's just computational basis, and and U is the actual circuit.
I see. Does pi include all possible outcomes?
Yes, as a function of x. So for each x, you have a computational basis element if you want.
I see. So X identifies the state rho X.
Yes.
And then pi X is a corresponding measurement outcome.
Mm-hmm.
Okay.
So the idea here is you are measuring, for example, in a computational basis, but you allow for the parameter to influence also the quantum circuit. Okay. But you might as well take a state valued function class here. I'm putting a conjecture just because it seemed easier for me to understand, but maybe you're thinking of some application where the state is actually more motivated.
Right, but the objective of this problem is to learn UX, but you're associating pi X also with what you want to learn?
So, okay, maybe I should have done a couple of slides on this, but so you can you can decide that the objective is to learn just UX, and then you fix the projections. Okay, so for example, you can imagine that pi is fixed, and you just have a variable circuit, and you want to reproduce the outcome on a certain computational basis element. This is one way of thinking about it. But the example from imaging can be as well used for a circuit. So in this case, so it depends what you want to fix. So in this case, you could fix. So we have more freedom in computing complexity on the unitaries. Okay, you have less freedom on the states. But this might as well apply to a circuit problem. That's what I want to say.
Okay. Thank you.
Thanks.
Sorry, I have another question. Sorry, similar question. I think this kind of learning process has some outcome. So in that case, you need to make some measurement. Usually, measurement is described by P of M, but in your talk, I think there is no P of M. So what measurement you will done in your research, in this research?
I'm not sure I understand because I cannot hear you very well on the microphone. But so you seem to have a problem with the measurement. Could you please repeat again, Masaito, what the problem with the measurement is?
Usually, in the case of learning, we need to make some measurement outcome. So
Okay,
in this case, you need to make measurement, and measurement is described as P of M. But in your talk, P of M does not appear. So I'm slightly confusing. This is somehow related to the Mark's question.
Okay, so probably you're referring to the first work by Aronson from 2007, which is called Learning Quantum States.
But that paper is quite strange, so I did not trust that study.
Because in that case, he's trying to learn the probability of accepting. Okay, so in that case, he has quantum state, and he's trying to learn
quite unnatural. So somehow P of M element randomly generated. So this is very unrealistic.
No, sorry, I don't understand your point.
So I did not remember that his but the impression for Aronson's paper, his problem setting is different from the real situation.
So why do you think it's not it's too ideal?
Because in his situation, P of M element randomly generate, but usually this is not true, I think.
Okay, so you're saying that it's not granted that you have randomization here.
No. P of M element, so in your talk, P of M element is not appeared, does not appear. So quite strange. So X is somehow a parameter to generate quantum state. So this is okay. Depending on X, so the state generator generates state. This is okay. But later you need to make measurement to get some measurement outcome. Otherwise, you cannot get any information.
I'm not sure I understand, but yeah.
Offline or in the discussion room?
Just to reply, okay. I mean, the measurement you optimize over it, right? Because you have these copies of your quantum states, and you want to extract some information about it. So, I mean, they're not random. There is a prescribed procedure to do it. And maybe if you are referring to the candidates, that the candidates can be projection valued, then this is just a step to prove it for general quantum states. So you can think that the candidates are pure states, and then they're not measurements. We're trying to predict what is the closer pure state to the process you are seeing. Okay.
Okay, thanks again for this interesting talk. I think we have to move on to the next talk. Yep. So our next speaker is John Casamiglia.